Let's now consider an example of a function which is not a Lebesgue function or a Sobolev function. In fact, it's a Lebesgue function, but it's not a Sobolev function. In this case, as above, as before, omega is just a square. So it's a very simple square, just a unit square. Let's now consider the following function, u of x. Note that x is, as before, consists of two coordinates, x1 and x2. And we let this function be equal to the first coordinate x1 square. Square root of x1, sorry. So taking the integral of the square of u, we just find that the integral, this integral is equal to the integral of x1. And since the omega is from 0 to 1, we can just compute this double integral from 0 to 1 of x1 dx1 dx2, and this is equal to, is less than the integral of the constant 1, because x1 in this square, x1 is less than 1. So necessarily, since this function is less than 1, it must be, this integral must be less than the integral of the constant 1. And this integral is just the area of omega, which is 1. And of course this is less than infinity. So this means that u must be equal to, it must be an element of L2. So it's a Lebesgue function. However, let's prove that it's not a Sobolev function. How can we do this? Well, we take the partial derivative of u with respect to x1. Then we obtain this expression. Remember that u is equal to x1, the square root of x1, and taking the derivative of this guy with respect to x1, we obtain that the derivative is equal to 1/2 of x1 in minus 1/2. On the other hand, since this function is not dependent of x2, of course, then this partial derivative must be 0. So the partial derivative of u with respect to x2 is, of course, 0. So, well, if we just take the integral of the partial derivative of u with respect to x2, then we obtain that the integral of this square must, of course, be equal to 0, which necessarily is less than infinity. So, of course, partial derivative of u with respect to x2 must be an element of L2. But now check the other partial derivative. The integral of the partial derivative of u with respect to x1 is equal to this. And when we are squaring this guy, we obtain x1 in minus 1. And this integral is equal to this double integral. And when we are taking the integral, this integral with respect to x1, we obtain the antiderivative of x1, or 1 over x1, which this is just ln, the logarithm of x1. And we know that integrating this logarithm from 0 to infinity, that means that from 0 to 1, we just put the the boundary values here from 0 to 1, and first we replace this expression by ln1 minus ln to 0, but 0 is minus infinity. ln to 0 is minus infinity. So then we obtain that this integrand is infinitely large. So then we obtain that this integral is infinitely large, which means that the function, the partial derivative of u with respect to x1 is not a member of L2 of omega. So, and you remember that we must have all the partial derivatives belonging to L2 in order to get the Sobolev function. So this means that u cannot be a Sobolev function. It's not a member of this function space.